So this week we are carrying on studying second-order differential equations, specifically second-order linear differential equations, but now we're going to look at the non-homogeneous case, whereas last week we just had a look at the homogeneous case. So just to remind you what we're looking at, there are differential equations that look like this. So last week we considered the case where f of t is just equal to 0. Now we're going to let f of t vary quite a lot. So the first question to ask is, what kind of situations might you find differential equations like this? And we can actually expand on the model that we looked at last week. So last week we said, well, imagine that you've got a building and we want to think about how it might move. So we modeled it very simply. Over here we actually had a dash pot that we put in. And we put together the differential equation, which looked something like this. So there's no additional force. We're just imagining our building. If we think about, if we somehow manage to just like move the mass a little bit away from the equilibrium position, what are the forces? How would things react? Well, this is the differential equation that we built up that would define that. And because we spent most of last week figuring out how to solve these, you could find that the displacement of that little mass follows an equation like this. And if you put in some initial conditions, so a little displacement a little way away from the equilibrium point and an initial velocity of 0, then you can find an exact solution like that. And if you plot what this displacement, so we're thinking about the displacement of this mass here around the equilibrium point, if you plot what that looks like, so if you plot this solution here, what you get is this. And you would kind of expect that that's sort of what you would think. You have an initial displacement, but the forces within the building, the spring force and the elasticity, are going to pull it back into position and damp that motion down. So you get a motion starting at your initial point, swinging back past through the equilibrium, but not as far on the other side, swinging back again through the equilibrium, even less far, and gradually damping down until the building has become stationary again. So that you could imagine perhaps that would happen if you got just a little gust of wind, might do something like that, and your building immediately stabilizes itself. But suppose instead that you have something like an earthquake. Now, earthquakes are kind of periodic phenomena, at least over a short amount of time. They kind of come and go in waves. So if you think of that as moving your building, we need to think about adding in a driving term, as it's called, to our differential equation. So in this situation over here, when we were dealing with this equation here, the only forces acting on it were the forces within the building itself. But now we're adding another force, which is the force produced by the earthquake on the building. And the question you might ask, so the left-hand side of this equation is exactly the same as we saw previously, but now we've got this term over here instead of a 0. And the question is, how much of a difference does that make? Can we solve it? So we'll come to how you solve this in a moment, but for the moment, believe me that you can. And the solution that you get looks like this over here. And if we take simple initial conditions, so we're saying there's no initial movement, there's no initial displacement, there's no initial velocity. So our building is standing perfectly still, and then the earthquake starts. What happens? Well, the displacement is going to look like that. And it might look like a lot of terms, but you can actually see that there are two distinct kind of types of terms. So if you look at these terms over here, both of these terms have an e to the minus t. And we know that e to the minus t damps down very quickly to 0. So those terms are what we call transient terms, because they will, although they have sinusoidal components, their amplitudes damp right down, so that after a very short amount of time, those terms basically become negligible. On the other hand, we have we have these terms over here. Let's just change that color. We have these terms over here, and those are purely trigonometric oscillating terms. So they are terms that have a certain amplitude, and that amplitude doesn't decrease over time. They just keep oscillating. So we get quite a different looking solution. So I've plotted over here again. This is with f of t is equal to 0 that we just saw previously. And here you can see, if you like, the effect, the transient. It would have been slightly different up here. So we would have had a similar transient there. We get a slightly different solution because we have different initial conditions, but you would get the same effect here. So here's our e to the x damping down. So that's when f of t is equal to 0. But when our f of t is equal to 10 to the 4 sine 5t, so now we're looking at this solution over here, what we get is we get an initial small damping there, but after that we just settle down into these very broad oscillations. And if you compare these two, in our f of t is equal to 0 case, we started with an initial displacement of 0.01, and that quickly damped down to virtually nothing. So that was after like 5 seconds. But if we look at our f of t equals 10 to the 4 sine 5t case, we start out with no initial displacement, but because of the earthquake we get this big displacement up to 0.03, and we don't get any dying down. So our displacement carries on being really quite high. And as long as the earthquake keeps driving this, our building will keep swaying. So these kinds of calculations are pretty important because they show that if you have a driving force, it can really alter the way in which your building behaves, or any other system that you have that's modeling. As soon as you put a driving term, as these terms are called, things change quite dramatically. So that's what we're going to spend this week looking at. So it turns out that we can use our solutions to the homogeneous differential equation as part of the solution to the non-homogeneous case, which might sound a bit strange, but true. So the trick, the way that we're going to go about finding a general solution to the forced equation, is kind of a three-step process. The first is we're going to find the general solution to the homogeneous ODE, so the one where f of t is equal to 0. So that we in fact already know how to do. We spent a lot of time last week doing that. So that we're going to do. The next thing that we're going to do is we're going to find one particular solution to the forced DE without thinking about initial conditions. So remember, a general solution is one that has the constants in it that enable you to solve for any initial conditions. But a particular solution is one that just works for this specific DE and can't be generalized to any initial conditions. You'll see what I mean in a moment. So this is something that we need to do in today's lecture. And then it's going to turn out that the general solution to our forced equation is going to be our general solution to, sorry, that's the wrong one. It's going to be our general solution to the homogeneous equation. So that's going to have its C's in, plus the particular solution to the forced equation. So the other thing that we need to do is do a quick check. Does this make sense? So the two things that we need to do is we're going to show that if we can find our general solution to the homogeneous equation and a particular solution to the forced equation, then a general solution is actually given by this. I don't want you to just take my word for it. We're going to show that. And then the next thing we're going to do, which takes up most of the time, is find out how do we find these particular solutions. Okay. So you've seen proofs like this before. I'm going to sketch it out for you. So what we want to do is we want to show that if we have a general solution to the homogeneous equation and a particular solution to the non-homogeneous equation, then the claim, which we want to prove, is that if I add those two solutions together, the result is a general solution to the forced differential equation. And the way that one usually does this is one just substitutes in. So we've got our u, which we're forming from our two solutions. I'm just going to rewrite this as C1 U1 of t plus C2 U2 of t plus UP of t, because remember our homogeneous solutions always have two terms like that. And now let's just differentiate it, because when we plug it into the differential equation we'll need first and second derivatives. So here comes first derivative. Okay, so this is a pretty straightforward proof. Let's take a second derivative. And now we're going to plug all these into the left-hand side of this equation here. And the hope is that once we work through that left-hand side, we should get f of t, in which case we know that the left-hand side equals the right-hand side, and we've found a solution. Okay, so we will have, gosh, this is going to be a bit of a pain, but here we go. We're going to have m times this whole thing here, and I'm going to change this very slightly in my writing here. I'm going to have m times the homogeneous terms, and then I'm going to have an m here, so I've just distributed the m a little bit. Okay, plus, and I'm going to do the same thing. I've got a c, which is my c from here, and let's grab this bit. Okay, and play the same game again, so c times those bits there, and a c there. Let's tidy this up. And then finally we've got to have plus k times our original bit over here. And again, I'm going to put the k in there, and we're good to go. Okay, so this is our left-hand side, and it looks like this. And now we can do a little bit of rearranging. Now you'll notice that if I look at these terms, those terms are really just m UH of t plus c UH of t plus k UH of t. And if I look at these terms, those will just be plus m, our particular solution, so we should have a double dash there, plus c plus kp. So that's, this bit is equal to this bit. Now, what do we know? This bit is the left-hand side of the homogeneous differential equation. So we know that this bit must be equal to 0. And this bit over here is the left-hand side of our forced equation, our non-homogeneous equation. But because we know that this is a particular solution, we know that it's a solution, and therefore this must be equal to f of t. And so adding those two together, we get that our left-hand side equals f of t, which is the right-hand side of our original differential equation. So we haven't quite finished yet. All that we've shown is that this crazy thing here, this constructed solution, is a solution to the forced differential equation. But what we specifically want is a general solution, which means that we can solve it for any initial conditions. But the thing to note here is that we have in our general solution here, we have a C1 and a C2. And because we have those two constants there, for any two initial conditions that we find, so for example an initial displacement and an initial velocity, given those, we can find values of C1 and C2 that will give us a particular solution. So that would be something that you could do if you were feeling like doing some maths. You could show that for any u of naught equal to A and u prime of naught equal to B, you can find C1, C2, so that u is a solution. And you would find your C1 and C2 in terms of your A and B. Okay, so we have quickly ticked off the first thing that we needed to do here, which was to show that this crazy idea that we have of combining the homogeneous general solution and a particular solution to the forced equation is a solution. Now we need to know how to find a particular solution to the forced differential equation. So here I've just summarized what we've got. It's a theorem. Okay, so how do we find a particular solution? So remember, we're trying to find a solution to something like this. So the quick thing is to think about what we know about derivatives. So for example, if we take a moment and quickly write down the answers to these. You should be able to do this very quickly. See if you can do it before I'm done. So we've got minus cos of t, and that will be minus sine of t. That's a 2t, that's a 2, that's an e to the t, and that's an e to the t. So what do we notice about this? So the thing to notice here is that if you are taking the derivative, whether it's a first or second derivative of a sine of a trigonometric function, you end up with a trig function. So if you start out with a cos or a sine, you're going to end up with a cos or a sine. They might flip, but you don't suddenly start getting exponentials. Similarly, if you start out with a polynomial, if you keep taking derivatives, you keep ending up with polynomials. They're lower order polynomials, but they're still polynomials. Again, they haven't become trig functions or exponentials. And again, with exponentials, they just stay exponentials. So if you have a look at the kind of thing that what are we saying over here? We're saying we want to find some function which is really a sum of second derivative, first derivative, and initial function. And these are all likely to have the same form, because we've got our initial function, we've got its first derivative, we've got its second derivative. So if, for example, our original function is a cosine, then this will be a sine, this will be a cosine. So they're staying within the trig function. So if we want our left-hand side to be equal to our right-hand side, or vice versa, it makes sense that we should try a solution that looks like the right-hand side. So if our right-hand side is, for example, a cosine, then chances are that some of these terms over here must be sines or cosines, because we couldn't be taking derivatives of something over here that was sines and cosines and then ending up with something that was not a cosine there. Not sure if I made that clear, but it'll come as we go. So the idea of what we do is we look at the form of the driving function and we try a solution of that same form. This is best seen through a bunch of examples. So we're going to find particular solutions to this differential equation, pretty straightforward one, for different values of f of t. So first we're going to say, suppose our driving function is just a constant, a 6. See what we do. Then we're going to look at a polynomial, then we're going to look at an exponential, and we're going to look at a trig function. So let's dive in and you'll see how this works. Okay, so we want to find a particular solution to our differential equation, and our f of t here is equal to 6. So we're going to try a solution of the form So I'm letting this be a constant, but I'm not fixing it. We're going to solve for that particular constant there. So you'll notice that we're doing this thing again where we're doing some kind of cunning thinking and then trying a solution, and we'll see if it works. So we're trying a solution of the form u is equal to some constant. Okay, well, what does that mean? That means that our first derivative is going to be 0 and our second derivative is going to be 0. So if we plug this into our differential equation, what do we get? So I'm calling this star. Well, we've got u double prime, so that's going to be 0 plus 4 times 0 plus 3 times a must be equal to 6. So that tells me, oops, equal to 6. So that tells me a is equal to 2. So in this case, my claim, so our claim is that u of t is equal to 2 is a particular solution to star. And if you double check it, you'll see if I take the second derivative of 2 is 0, the first derivative is 0, so I'm just going to get 3u, which is 3 times 2, and that will give me 6. So it is definitely a solution. Okay, so that seemed to work and probably seemed to look strangely easy. Let's look at another example. So in this example, we've got a slightly more complicated forcing term. So here f of t is a quadratic. So what we're going to try is a solution of the form also a quadratic, but where the coefficients are for us to determine. So we're going to try a form of the term, a solution of the form a plus bt plus ct squared. And because these are coefficients that are unknown, this leads to the name for this technique, which is the method of undetermined coefficients. Okay, so if our solution looks like this, then we need to be able to plug it into the differential equation and have it solve the differential equation. So let's try that. So we're going to need the first derivative, which is going to be b plus 2ct. And we're going to need the second derivative, which is going to be 2c. Now we're going to plug these into our original dE. So we need to have 2c plus 4b plus 8ct. So those are those two terms plus 3u, so that's plus 3a plus 3bt plus 3ct squared. And we need that all equal to 12 plus 11t plus 3t squared if this u of t is going to be a solution. So if we do a little bit of rearranging, we'll see that we've got some constant terms. So we need to have 2c plus 3a, done with those, plus 4b, okay, 2c plus 4b plus 3a. Okay, so there are my constant terms. Now I'm looking at my t terms, so that's going to be plus 8ct plus 3bt, and finally I've got a 3ct squared, and this has to be equal to 12 plus 11t plus 3t squared. So if we look at the left and right hand sides of this equation, we can see that our constant term, our 12, must be equal to our 3c plus 4b plus 3a, because the other terms on the left hand side all have t's in them. So we end up with an equation that says 2c plus 4b plus 3a is equal to 12. And now we look and say, okay, well, here are our t terms, our 8ct plus 3bt, and that must be equal to 11t. So that gives us that we must have that 8c plus 3b is equal to 11. And finally, we can do the same trick with our squared, our t squareds. We can see that we must have that 3c is equal to 3. And you'll notice that conveniently we've got 3 equations and 3 unknowns, so we can solve these however you prefer. We've got this one over here, tells us that c is equal to 1, so that makes life quite a lot easier. So we can then plug that into 8 plus 3b is equal to 11, which gives us that b must also be equal to 1. And then finally that gives us that 2 plus 4 plus 3a is equal to 12. So that's a 6. So 3a is equal to 6. So we must have that a is equal to 2. So finally, and I'm just going to check my notes to make sure that I did that correctly. I did, hooray, okay, yes. So finally, we claim that this solution, u of t, equal to 2 plus t plus t squared is a particular solution. And if you were to differentiate that, you would find that it does actually work. So notice here we're only finding a single particular solution to this equation over here. So it's not a general solution, and we haven't even talked about initial conditions. So that's why when we find the general solution to the differential equation, we bring in the solution to the homogeneous equation, which gives us the constants, which we can then play around with so that we can find particular solutions for any initial conditions. So this is not the whole solution. Here, all that we've done at this point is find the particular solution. We will look at a final example where we do it all. What we'll do is we'll find the solution to the homogeneous version, so where f of t is equal to 0, so that gives us some constants and some terms. Then we find the particular solution like we just did, and then we add them together, and that's our final general solution. But for the moment, we're just focusing on finding the particular solution. Okay, let's have another example. So we try the same trick again. So we try a solution of the form a e to the minus 5t, because our f of t is e to the minus 5t. And we do what we've just been doing all along, so we take the first derivative, so that's going to give us a minus 5a, whoops, e to the minus 5t, and our second derivative is going to be 25a e to the minus 5t. And if you plug that all in to, let's call this 2 stars so we don't get confused. What do we get? I'm going to do some pre-bracketing here, so you're going to get 25 minus 20 plus 3a e to the minus 5t is equal to e to the minus 5t. So that's just rearranging some terms, from which you can conclude that this bit must all be equal to 1. So we must have that 8a is equal to 1, so a is equal to 1/8. So a particular solution in this case is 1/8 e to the minus 5t. Okay, one more example. So we could look at this and go, okay, well, it worked pretty well in the past to try and find solutions that look almost exactly the same. So you could try u of t is equal to a sine of 2t. But if you try that, you'll run into trouble. I suggest you do it just once. But it's going to turn out that when you have trig functions, because trig functions swap between sine and cosine with the differentiation, what you're actually going to want is you're going to want a sum of a sine and a cosine. So this won't work. Instead, we're going to try u of t of this form. We're going to try a sine of 2t plus b cosine of 2t. And if you plug this all in, so you'll notice this has given us two constants. Over here we only had one constant, here we had three constants, so nothing particularly strange about that. It's just going to turn out having the two constants works really well. So you can work out for yourselves what the first and second derivatives will be, and again you substitute in. And if you do this, and I recommend that you do, you should find that, let me have a look at my answer here, a is equal to -1, oops, no, that's not the right a, should have a is equal to -1/65, and b is equal to -8/65. So that our final solution in this case is -1/65 sine of 2t minus 8/65 cos of 2t. Okay, and again you could double check that this is actually a particular solution by doing all the differentiation again, but you probably don't feel like differentiating anything ever again right now, so you don't have to. Okay, so let's just summarize what we did. We were looking for solutions to, so far we've actually only found particular solutions to this differential equation here for different values of the driving function. So when our driving function was 6, we found this particular solution. When it was quadratic, we found this. Here's an exponential and here's an exponential. Now, from last week, you could find the general solution to the homogeneous version. I encourage you to do that. This is one of the cases where we have real roots, so we have two decaying exponentials. So our homogeneous solution looks like this. So finally, if we want our general, so if we want the general solution to that differential equation, here we have for each of them. So when our driving function is 6, our general solution looks like so. And I've plotted over here in grey this is my specific solution when the driving function is just 6, and the general solution for those values of the constants look like this. On the other hand, when our driving function looks like this quadratic, our general solution looks like so. So here's our driving function, and if you plot this particular version for C1 equals 1 and C2 equals 1, then your final solution looks like this. So quite a different look to when you just have a constant driving function. Similarly, if we have our exponential, so as our driving function, then you will end up with a solution that looks like the green line. Sorry, this should be our, there's our green line, our exponential. And finally, if our driving function is a sinusoid, then you end up with a solution that looks like a decaying exponential with a sinusoid on it. What you want to take away from these pictures is that the way that your solution looks depends hugely on your driving function. So obviously the kind of force that you're applying to the system is going to have a big effect on how its motion is going to change. So just to summarize, so I didn't mention the word, but it's the same idea that we had last time. We've been using ansatzes, which are basically educated guesses. There are good ansatzes that can always help you. So for example, if your f of t is a constant, try a constant. If it's a polynomial, try a polynomial of the same order. Exponential, and we saw if you have something of the form a cos omega t plus b sine omega t, so we only had a cos omega t, but you're pretty much always going to need two terms. Things that we haven't looked at, you might have a driving function that's a combination of an exponential and sinusoids, in which case try the same form. And again, exponential combined with a polynomial, try that same form. And finally, trig functions combined with polynomials, try the same form. So on the whole, these would be good ideas to try if you're trying to solve for forcing functions. You'll notice that there must be forcing functions that we don't have ideas for here. So obviously this is not a technique that works for all differential equations, but it does work for many. So the next thing you might ask is, well, what happens if something that we try doesn't work? So let's see, because there are always tweaks that we can make. And in fact, it's a tweak that you've seen us make before already. So let's have a look. It's our good old differential equation here that we're learning to know and love. And here's our driving function. It's an e to the minus t. So notice that if you followed what we just said in the table, you would try a particular solution of this form here. So some constant times e to the minus t. But if you plug that into the differential equation, then you would get 0 is equal to minus e is e to the minus t, which just doesn't happen. So that's not a starter. We can't find an a that makes this true. And the reason for that is because if we put our particular solution equal to a e to the minus t, then that is actually that our particular solution, which is supposed to be a particular solution to a non-homogeneous version, is actually a solution to a homogeneous problem, which it can't be. So there's a problem. What can we do? Well, we try what we've tried before. So we're going to take something of this form, but we're going to let a vary with time. So instead of having it a constant, we're going to have a vary of time. So remember, we did this when we had the identical roots case, when we looked at things last week. So let's try u of t equal to a of t e to the minus t. And let's see if we can figure out what that a of t should be. Well, we do what we've been doing all along, so now we find our first derivative. And now we have to be careful, because when we take this derivative, remember a is a function of time, so we've got a dashed of t e to the minus t. So that's the derivative of the a of t. Now we need a minus a of t e to the minus t. And now we take the second derivative. And now we've got 4 terms in our derivative. So we've got an a double dashed of t e to the minus t minus a dashed of t e to the minus t minus a dashed of t e to the minus t plus a of t e to the minus t. Okay, I think I did that all right. Okay, and now we plug those all back into the original differential equation. So we have an annoying number of terms, but here we go. Okay, so we have a double dashed of t e to the minus t minus. Okay, so I'm going to combine these two terms here. That's minus 2 plus a of t to minus t. So that's the u part. Now we've got plus 4 of this. Okay, so that's that term plus 3 times u and this whole thing has to be equal to e to the minus t. So let's just carry on simplifying. So this is our left hand side. So this is equal to, okay, I don't have any other terms with the second derivative of our a, but let's have a look. What do we got for our for our first derivative terms? What have we got? We've got a first derivative term here, a first derivative term here. So that's plus 2 e prime of t e to the minus t. And now we've got our terms that just have a's in them, and we see that they actually cancel. So that's pretty nice. So we're left with a double prime of t plus 2 a prime of t e to the minus t on our left hand side. And you need all of this must be we must have that this left hand side is equal to the right hand side if our proposed u of t is a solution, from which we can conclude that this term over here must be equal to 1. So we must have and so finally we can solve this differential equation here for our a of t, but that's quite a lot simpler than anything that we've had up to now. So the thing to remember here is that we are just looking for a particular solution. Anything will do. So if we can find any function a of t which makes this equation true, we can use it up here and we'll be golden. So you could think through some possibilities, but one really simple thing would be to say, well, let's let a of t be just a simple linear function of t. So let's have a of t. Then our first derivative is going to be equal to a, and our second derivative is going to be equal to 0. So if we plug that in, we get 0 plus 2a is equal to 1, and we get a is equal to 1/2. So our function a of t equal to 1/2 t will do. Putting this all back together, our particular solution is up of t equal to 1/2 t e to the minus t, based on this up here. And you'll see that this was a very similar technique to the one we used for finding an additional solution to our double roots case. There were many more options, so you could have decided, instead of taking an a of t of this form, you could perhaps have tried a quadratic and you would have found something else. So there are many correct answers. Just go for the simplest one would be my advice. Okay, so we have now answered basically the essential questions that we needed for this part of the problem, which was how do you find a particular solution and how do you use that to make a general solution to the forced case. A few more things that you might be wondering. So can you apply these techniques that we've used to higher order differential equations? And the answer is absolutely. So for example, if you have a third order ODE, you could try it with the same form there, And then all that you'll do, you'll realize instead of getting a quadratic as your characteristic equation, you'll get something of order 3, a polynomial of order 3, which will have 3 roots. So you need to go through the same sort of process that we did. It gets a little more complicated, particularly as you go to 4, 5, 6 roots, because then you can get different multiplicities and you have to learn how to deal with those. But the basic techniques you've got here. And if you need to do this at any point, reading the notes should, and kind of reading whatever material, should seem relatively familiar to you. And similarly, the non-homogeneous case can also be handled using undetermined coefficients for higher orders, exactly the same trick. There is another way though, and this we will talk about a little bit when we talk about systems of equations. So for higher order differential equations, you can sometimes break them down into systems of lower order differential equations, and sometimes that makes them easier to solve. We haven't really talked about variable coefficients, but we can look at these using series methods. So often we'll take a u of t as a series and then find what the coefficients should be like that. So if you haven't really worked with series, don't worry about it. This is just to give you a flavor of how you might deal with it. But again, we're using this idea of positing a solution, so using an ansatz, and then taking that ansatz and figuring out what the coefficients should be. So this is for cases where we have variable coefficients. As soon as you get into second and higher order nonlinear ordinary differential equations, there are no techniques that work for everything. It's a very kind of broken up field where, depending on the very specific form of your differential equation, you will use very specific techniques. We might get to talk a little bit through some techniques that can help later in the course. So, why am I still talking? Because there is a little bit more to be said here. So I'm going to end this video shortly, but where we're going to head now is looking at the phenomenon of resonance. So you've probably heard a little bit about this, but this is really analyzing in some detail what happens for specific driving functions. So we've seen that you could have very different responses depending on whether you have a flat driving function or a sinusoidal one, and it turns out that with sinusoidal driving functions there's actually a lot of interesting stuff that happens. So the second part of this video will be about resonance and looking at that in a little bit of detail. But for the moment, just spend some time getting comfortable finding particular solutions depending on particular driving functions. And when you're happy with that, come back and learn about resonance.